In this video, we're going to be examining balance factor height AVL trees and the process of trying to get a AVL tree to be perfect by using the concepts of rotations. So first, we're going to get a tree, and then we're going to compute the heights, compute balance factors, identify the first unbalanced node, determine the rotation cases required to fix that node, and we're going to perform those rotations, and then we are going to find the final AVL tree. So let's start off with our tree. Let's say that we have a tree that looks like this. So we're going to just draw this tree, and you can draw it along with me. 50. So let's start with computing the heights. When you compute the heights, you do this from bottom up. So let's start off with the leaves. So our leaves in data structures, what we define their heights to be is they will always have a height that is equal to 0. And a leaf has no children, so you can easily identify those by looking. Now let's start off with our next level that is not a node, that is a leaf. So computing the heights for node 20. On the left, your height is 0, or your height is 10. You have a height 0. The height of node 10 is going to be 0. And then on the right, it's null. Just like these all are null. These are null, right? That's null. So for 20, you can write and for your balance factor, you're going to take your height of your left minus your height of your right. So that's balanced. Now let's look at 35. 35, your height is equal to 1 plus max, 0, negative 1. That's equal to a height of 1. Now for balance factor, that's equal to 0 minus negative 1. That's 1. That's balanced. 35 is going to be balanced. Now let's examine 40. So for 40, on the left, your 35 node has a height of 1, and on the right, you have null. I'll actually do the balance factor in a different color. Okay, so now for 90. For 90, now I'll move on to 30. Now for 80. For 80, But before you do 80, we have to do 70. We have 70. That was h is equal to 0. So for the balance factor of this, that's because our h here was 1 plus, and for 50, so now what it means when you have an AVL tree is your balance factor has to have an absolute value that is less than 1. So that means it can be 0, 1, -1, but not out of this. And where does this break? So that's our requirement. Where does it break? We see it breaks here because the balance factor is 2. So now let's examine this tree, this subtree. Like, what is going on here? Why is there an issue? So examining this tree, we can see that this is where our first rotation must be, and there is a path of imbalance. So it's a heavy left direction. So when you have a heavy left direction, that means you have to do a right rotation. So let's rewrite our subtree so we can really look at this. You have 40. So you're going to do a right rotation around 40. So what is going to happen is 35 is to become the new root. 40 becomes right child of 35, which is the new root. New root. And 33 becomes the right. 35 sub, and okay, no. We note that 35's so what's the result of this going to look like? So now you have to reattach it to the parent. So let's take this and let's take our tree and reattach it. So this is what we're taking out. So this is your tree after the rotation. So now after this, that we have our fixed after rotation, let's calculate our new heights. Node 20 it's gonna stay the same. You're still gonna have this as your height and your balance factor is 1 because you didn't change anything on this side. So really we're only looking at this split right here, this division of 30. That's where your heights are really going to change, and anything around there. So 35. 35's balance factor and height. For the leaves, balance, and height, they're still 0. So let's look at node 30 or node 90. It's still going to be 1, node 30. Now you have a left that is 1 and a 35, where 35 is going to be a height of 1. Actually, so you have to add 1 to that. So for 30, 1 plus 1, so balance factor is going to be changed. So you have, on your left it's still 1, and on your right you're going to have one, so that's equal to 0. Now, what about 80? It's still -1. And what about 50? So for 50, your height is going to equal to 1 max of 2 and 2. And your height is going to equal to 3. So then your balance factor, 3 minus 2 is, no, not that. On your left, you have 2 as your height, and on your right, you have -2. So combining those is going to give you just 0. So now your final AVL tree, all nodes satisfy. So it's a valid BF tree and also a valid AVL tree.